The title of my talk is Arnold Conjecture over integers, and what I'm going to present today is based on joint work with Guangbo Xu. So let me give you an outline of my talk. So it's going to be 3 parts. In the first part, I'm going to state the result and maybe add some discussions about my point of view of Arnold Conjecture. In the second part, I'll give you a proof outline. In fact, I would say it's an outline of an outline because, well, there's many things to talk about. And then in the third part, I'll give you some selected technical details. I think I'll try to convince you that there are some tools you could perhaps borrow from the things we use. For this talk, I'm going to look at a closed symplectic manifold. Is a manifold, and omega is symplectic form. And I'm going to look at Hamiltonians. So one periodic, spelling. One periodic smooth Hamiltonians. And as usual, I denote such a thing using the notation H sub t. And from that Hamiltonian, we can cook up its Hamiltonian vector field. Which is defined to be the symplectic dual of the differential of this Hamiltonian. And I take this convention that, well, I put this vector field on the first coordinate of symplectic form. It's a matter of convention, it doesn't matter. And going from the Hamiltonian vector field, we can construct the type 1 flow. Of it, and I use a notation phi ht1 to denote the type 1 flow of ht, and this is associated Hamiltonian diffeomorphism of Hamiltonian ht. So today's talk is about the non-degenerate version of Arnold conjecture. So in particular, we assume that for any fixed point of the Hamiltonian diffeomorphism, if we look at its linearization, it doesn't have 1 as an eigenvalue. So to say in words, all fixed points are non-degenerate. So the goal of today's talk is to find some kind of lower bound for the number of fixed points of this Hamiltonian diffeomorphism, which is what the Arnold conjecture is about. Okay, so let me introduce some other notions before I state the result. So here, let me use the number n to denote the minimal Chern number of our symplectic manifold. So in other words, n is defined to be the maximal positive integer. It could be infinity. Such that if we divide the first Chern class of my symplectic manifold by the number n, it's still an integral cohomology class. And remember that for any symplectic manifold, we have a contractile space of compatible almost complex structures. So that could endow us the tangent bundle of M with a complex structure. And the first Chern class is defined to be the first Chern class of this complex vector bundle. Okay, so now we have an integer n, and going from there, let's cook up some kind of integral homology of our manifold. So in short, so let's consider this version. So star is some kind of element sitting inside the group Z modulo 2n, and n here denotes this kind of n we take. So its definition is given by, let's look at all the integral homology groups of M, and I take the direct sum of all of them, whose gradient here is congruent to star modulo 2n. So in other words, I'm looking at the integral homology of M with this kind of reduced Z mod 2n grading. So in particular, for example, if your manifold has minimal Chern number given by 1, so we are just assemble the integral homology groups into the even and odd parts. And in any case, this is still a finitely generated module over the integers. And remember that Z is a principal ideal domain. And by what you learn from your maybe first year, second year abstract algebra course, you know that it has a structural theorem. It says that we could find a non-negative integer b together with a sequence of positive integers and I denote all of them by A1 up to AK. So I think in the literature is usually called the invariant factors. Such that our integral homology group has such a form. It's isomorphic to the direct sum of the free Z module of rank B plus some torsion parts. So that's its form. So using this structural statement, we can define some kind of numerical invariant out from this homology group. What we do is we take the sum of B, which is the rank of free part, together with 2 times K. So let me explain. 2 means that to find a chain complex over Z with homology of the form, say, Z modulo K, sorry, let me say AI, we need at least 2 generators. So that's why each torsion part should contribute to 2 of our count here. Okay, so I've defined this Z mod 2n reduced version of integral homology. And I mean, in the sense of collapsing the gradients. And from each of these homology groups, we define some kind of numerical invariants taking account of both the free part and the torsion part. With these preparations, I can state the main theorem. So suppose we have a non-degenerate Hamiltonian defined over our symplectic manifold omega, then number of the fixed points of its time 1 map is bounded from below by the sum of all of these integral versions of Betti numbers. Let me just write it here. So that's the statement. So let me add some explanations of this statement. It's because we are talking about integral homology. So by universal coefficient theorem, we can go from this integral version of total Betti number to Betti number over fields. We can recover results of in the case of where the ground field is Q, there's the work of Kai Ono and Liu Tian, and there's some other proofs. So the bound on the right-hand side of this inequality is given by the total rational Betti number. And if we look at field with positive characteristic, we can recover the recent result of Abouzaid-Blomberg. So their paper is nearly 200 pages. Our paper is nearly 200 pages. So I think, well, we cut it in half. So, okay. All right. So, but of course, this lower bound is stronger in some cases. For example, if the torsion components so stronger if the torsion components of our integral homology groups of different characteristics or different, well, let's say things like this. This is an example. For example, our torsion components is of the form Z mod P, where P is a prime. So in this case, if we have an example that those parts with different when I say different, I mean different gradient. You can see that on this lower bound is better than the bound from Abouzaid-Blomberg's result. Okay, so this is statement. Is there any question? Good. Of course, when we talk about Arnold conjecture, I'd like to mention some history. This is a very incomplete list. Of course, theorems. My internet is connection is unstable. Historically, statement of this form was first established by Conley-Zinder in the case of two-dimensional torus. And then, of course, there's a breakthrough of Floer, which established such a lower bound for monotone symplectic manifolds. And in particular, Floer invented Floer homology to deal with this kind of problem. And so let me say monotone. Then in the case of, say, Calabi-Yau's or more generally semi-positive symplectic manifolds, there's a proof by Ono and Hofer-Salomon. So semi-positive. Then there's a work of Kai Ono, Liu Tian, etc., using virtual techniques to prove such a estimate for general symplectic manifolds, but with rational Betti numbers at the right-hand side. And of course, as surveyed before, there's a work of Abouzaid-Blomberg. And here's the state of art of this conjecture. I mean, at least for the non-degenerate version. Okay. So let me add some discussions about this statement before I talk about something about the proof. So as you could see from the statement, we need to collapse the gradient from Z gradient to Z mod 2n gradient. And because of that, there might be some kind of torsion components which are collapsed to the same component after this kind of collapsing. For example, if we're really unlucky, for example, if our minimal term number is given by 1, then let's say we have a torsion component of the form Z mod 2 in H7 and the torsion component of the form Z mod 3 in H9. Then after collapsing the Z gradient to Z mod 2 gradient, they will contribute as Z mod 6 in H odd. So in this case, although we have two different torsion components from the Z gradient point of view, they only contribute to our lower bound. So you could criticize that, well, why don't you prove that lower bound could be given by the statement, this kind of quantity you cooked up without collapsing the gradient, but the problem is we have to use Floer homology. And I think it's an interesting question to think about whether one could improve this kind of lower bound by going from Z mod 2 n gradient to a Z gradient. Or on the other hand, one could think about whether there are potential counterexamples that tells you that you have to collapse the gradient to get lower bound. So that's one part of the discussion, which is about the collapsing of gradient. And there's another part. So this is about the homological version of non-degenerate Arnold conjecture, and there's a lot of variant of this type of conjecture. And of course, it's not clear to me whether the original version of Arnold conjecture in the non-degenerate case with lower bound given by minimal Morse number is really approachable at this moment. But I think the version of stable Morse number as the lower bound might be approachable. So what does it mean? Well, stable Morse number, let me remind you in case you're not familiar with that. So it means that we consider Morse functions defined over the product M cross R to the K such that it's quadratic at infinity. And the stable Morse number is defined to be the minimum number of critical points of all such functions. So of course, we allow K to vary. And then you could conjecture that such a number could serve as a lower bound for a number of one periodic orbits of a non-degenerate Hamiltonian on our manifold. So why I think it might be approachable? Because, well, perhaps you could develop some kind of bifurcation method to understand the simple homotopy type of our Floer chain complex. And discuss about, say, what type of torsions cooked up from this kind of construction. And in particular, if your target manifold is simply connected, it is true that in this case, the stable Morse number coincides with the Morse number. Okay, that's a discussion about the statement of theorem. So, is there any questions? No? Okay. So this finishes the first part of the talk. So now let me move to the second part, which is about an outline of the, well, proof or an outline of the outline. So in one sentence, the proof is based on defining Floer homology over the integers. So let me give you a slightly more precise statement of what we want here. So let me use the notation lambda sub z to denote the Navikov ring with integer coefficients. Then we can state our theorem. So still, let's fix our symlectic manifold M omega, and let's assume that we have one periodic non-degenerate smooth Hamiltonian. Then we can find a chain complex defined over our integral Navikov ring. And for those of you who care about energy filtration, as usual, this is a filtered chain complex. And this chain complex has a feature that it's Z-mod to N graded. So it's graded by the Conley-Zinder index of the capped orbit, and it's freely generated. Over our ground ring. By the fixed points. Sorry, there's no number here. So this is usual construction of Floer theory. This is just the chain complex which induces the Floer homology. And the point is we can define it over the Navikov ring with integer coefficients. So this would result in the Floer homology if we take the homology of this chain complex. So this is the first part of the statement. We can just define the Floer chain complex. And of course, to prove Arnold type conjecture, we need to compare that with some sort of homology of the underlying manifold. So the approach we take is to use PSS morphism. So to be more precise, it says that suppose we fix a pair where f is a Morse function and g is a Riemannian metric such that the pair is Morse small. Let's consider the Morse chain complex over the Navikov ring, which is just defined to be the integral chain complex with the base change, the Navikov ring. So once we define this chain complex, the statement says that there is a pair of chain maps, which is called PSS. Together with some sort of inverse. So I just reverse the order of the letters called SSP. So there are chain maps such that if I consider one side of the composition, so which means that it goes from the Morse chain complex to itself. So it is the form some kind of identity plus something with positive valuation. So in other words, if you filter your chain complex here according to the valuation given by the Navikov ring, then the composition of this pair of maps is upper triangular, and its restriction to a diagonal component is an identity map. So that's the statement. Then we immediately will derive that. So let's say we pass to the homology of both sides. So the Morse chain complex here is our Floer homology. Because the fact that it has some sort of inverse, this is an injection. The point is, if we have something of this form defined over our Navikov ring, it is invertible. So PSS has a left inverse, so it's an injection. So let me be more precise here. It shouldn't be equal, otherwise we've proved strong Arnold conjecture. It should be chain homotopic. Yeah, that looks better. Okay. All right. So if this map is an injection, then our statement, the integral version of Arnold conjecture, follows by elementary algebra. Okay. So there are some things you can say about the statement. Let me state them in the form of remarks. So as you can see from the statement, what we do is we just construct a chain complex, well, which defines the Floer homology, and we can compare that with the Morse. Didn't say anything about the invariance of this Floer homology if we change our Hamiltonian or some other underlying auxiliary choices in the definition. So indeed, we haven't established that. So we haven't. Established the independence of our Floer homology on the Hamiltonian, etc. So nonetheless, it's actually true in principle. The problem is, well, although we have all the tools, but to really figure out a rigorous proof of this invariance result, that would maybe perhaps add another 50 pages to the paper. So we can save it later. Okay. So that's the first remark. So the second remark is, in our proof, as you've seen before, we just define a chain complex over the integral Navikov ring, which don't really use Floer homotopy theory, as in the work of Abouzaid-McLean-Smith. But I would say our approach is conceptually related to the approach based on Floer homotopy theory. So perhaps I will elaborate on this point later when I talk about the technical ingredients. And there's a third remark saying that actually our construction of Floer homology over the integers could work. Oh, okay, I thought. Okay. So my Apple Pencil is out of power. So let me just say things in words and give it a minute for it to charge itself. So it says that, so this is about an integral version of Hamiltonian Floer homology. But my claim is this kind of construction could work perhaps also in the case of Lagrangian Floer theory. So in other words, the expectation is if we have a closed Lagrangian submanifold in a symplectic manifold and assume that Lagrangian is spin. So spin here is to get coherent orientations on moduli spaces of holomorphic disks. So the techniques here could presumably produce some kind of curved infinity algebra associated to this Lagrangian with integer coefficients. So, and of course, if you drop the spin assumption on your Lagrangian, the expectation would be we can define this infinity algebra over the ground ring Zima 2. So, okay, it's back. So, okay. So are there any questions about the statement and remarks? No? Okay. Right. So let me give you some kind of outline of the ingredients I need to establish the previous statements. So overall, it's based on two things. So firstly, we would need a new perturbation method to deal with, say, orbital kind of points in our moduli spaces, so that we could extract integral invariants out from them. And this method is actually part of that was worked out in the early joint work with Guangbo Xu, and we realized the proposal of Kai Ono. And second part is based on some kind of generalization of Abouzaid-McLean-Smith's recent development of some regularization technique of the moduli space of J-holomorphic curves. But we should do this in a Hamiltonian setting. So let me write something more concrete here. So for the first part, it's about producing integral. Okay, I think by definition, pseudo-cycles would provide you with integral moduli classes. So I put integral here to emphasize that. I'm going to write some big words here, and I will try to explain them later. From normally complex derived orbifolds. So what does it mean? It means that more or less we can produce integral pseudo-cycles from a space endowed with some sort of global Kornischi chart, such that the virtual tangent bundle, which is the difference of the tangent bundle of a thickened moduli space minus the obstruction bundle as a KO theory class, admits some sort of lift to the K theory. So in other words, we have a stable complex structure, but that's really not, but that's still too strong for our, as our assumption. So I'll explain it later. And for this part, it's based on earlier work with Guangbo. And but for Floer theory, what we've developed in our previous paper about Guangbo theory is not enough, because we have to show that this way of producing integral pseudo-cycles is multiplicative. Of the perturbation. So what does it mean? The point is, if we look at the modular space of stable Floer trajectories connecting a pair of capped orbits, and if we look at its sort of boundary, codimension 1 boundary of the modular space is given by the product of modular spaces of lower energy, in the sense that geometrically, we need to add broken Floer trajectories with at least 2 levels to compactify the modular space. So for our construction of perturbation, we do it inductively. So we construct some perturbations on the first component and construct some perturbation on the second component. We need to guarantee that their product is also a well-defined perturbation. It's not easy to prove at all. So this is something new we need to develop here. Okay, so that's about perturbation method. And the second part is about some regularization scheme of modular space. So in other words, what we do is we need to construct global Guangbo charts for the modular space of stable Floer trajectories. And for this part of the construction, there's also an archive post by Simon Rezchikov. He has a slightly different approach to construct the global Guangbo charts. And to make sure that the argument could carry over, we should also put smooth structures on our modular space. So in other words, okay, this pen doesn't work again. So let me still say this in words. So we need to construct smooth structures on modular spaces, and well, the differential geometric approach would be based on proving some kind of smooth gluing theorems. But as already presented in the work of Abouzaid-McLean-Smith, they actually use some kind of smoothing theory, which was developed by other topologists in the 60s and 70s to endow the modular space with smooth structures. So that's also the approach we are going to take. But in the case of Floer theory, we have infinite many modular spaces, and these modular spaces are usually manifolds with corners. So we need to develop some kind of smoothing theory.
Excuse me, I have a question. So you mentioned the work of Rezchikov, and what was kind of the goal of this work?
I think he has some other motivations, but somehow I think he has some other motivations to construct the global Guangbo charts in the setting of Hamiltonian Floer theory. And for him, perhaps what's already done there might be combined with our previous approaches, so he could do something out from that. So that's my understanding.
But something, I mean, I had an impression that he also claimed in Arnold Conjecture over integers, right? So he used it. I mean, what is your perspective on it?
Okay, so now everything is recorded, that right? So let me say things in this way. So I would encourage the audience to have a look at both papers, and I think in his paper it's also claimed that a version of this Arnold conjecture over integers is proved, but perhaps based on the one could try to tell what kind of technical details are presented there. And for us, I think his paper more or less contains a complete construction of global Guangbo charts. But for other parts, perhaps more technical details should be added to make sure that's a complete proof.
Okay, fantastic. Thank you very much.
Okay, thank you. Thank you for the question. Okay, so smoothing manifolds with corners. Okay, it's unreadable, but I hope I already said things in words. All right, so now let me move to the third part, which is about some more technical details. So I will try to highlight some things that we think would work in some other contexts. So now let me explain this kind of notion of normally complex polynomial perturbation. So what does it mean? So previously I mentioned derived orbifold. So what's a derived orbifold chart? So it's a way to package global Konishi charts, but let me use this language. So it's a triple where D is a smooth orbifold. E is a smooth orbibundle. And this is a continuous section. So locally modeled on equivariant sections. So, and we say a derived orbifold chart is compact, provided that the zero locus is compact. And of course, to put this into context, this usually would arise as global Konishi charts of moduli space of J-holomorphic curves. So in other words, the zero locus of the section, which you recall the Konishi section, admits a homeomorphism onto the orbit space of J-holomorphic curves. Okay. So now let me explain the meaning of normally complex. It means the following. It means that for any point in our orbifold, so let's choose the orbifold chart surrounding X, meaning that U is some kind of open subset in a Euclidean space. Gamma is a finite group acting, well, in our setting, we usually just care about effective orbifolds, which can be achieved for non-effective orbifolds or derived orbifold after putting some stabilization. So gamma is a finite group which acts linearly on Rn, which also fixes the open subset U. And this kind of C is a homeomorphism from the quotient to our orbifold. So let's take an orbifold chart. Then if we look at the tangent space of our orbifold, it admits a decomposition as a gamma representation. So the first component is given by the gamma fixed part of its vector space. The second part is given by the complement, in other words, the direct sum of all representations which are non-trivial. When we say an orbifold is normally complex, we mean that this part, sorry, what's happening? Okay. Okay, does anyone know how to make this thing go away? Oh, okay. Okay, fantastic. So when I say an orbifold is normally complex, we mean this part, namely these non-trivial representations are complex. And of course, I just described this kind of structure in the local setting. And for the global structure, we will require that they fit in with each other in a compatible way. But I will not go into the details. So similarly,
can you explain why is it important to have the normal part complex?
Yeah, so that's going to be one of the important assumptions in our perturbation scheme. So let me put things in this way. Because of this kind of complex structures, we could more or less perturb our Konishi section locally using algebraic sections. So complex polynomial perturbations. So that would allow us, so in that case, if we have some kind of complex algebraic variety, and we take its closure in some sense, this kind of boundary component you would add is of codimension at least 2 as in real dimension. Because of this kind of locus is sufficiently small, we could produce some kind of homology class just by looking at this part before you take the compactification. So, all right.
Thanks.
Thank you for the question. And similarly, not only for the underlying orbifold, we require that if we look at an orbibundle chart, and if we consider the fiber of our obstruction bundle as a gamma representation, we can also decompose that into the direct sum of 2 parts. This part is also required to be a complex gamma representation. So both the tangent bundle and obstruction bundle has complex normal part. So that's explanation of normally complex. Okay, so now let me state the abstract perturbation statement we want for our applications. So the setting is, suppose that we have a compact in the sense that the zero locus is compact, normally complex derived orbifold chart. Then it says that for any epsilon positive, we can find a section which is called, well, in our language, the FOP perturbation. And of course, to produce some kind of pseudo-cycles, we want some kind of transversality, so they are called strongly transverse. So I will not go into the details. So, but I will say FOP means Fukaya, oh no, Pucker. So Pucker is Brett Pucker, and it satisfies the condition that it's C0 close to our original Kornishi section. Moreover, if we look at the zero locus of our perturbed section and consider the open locus whose consisting of those points whose stabilizer is trivial, in other words, the free part, it defines a pseudo-cycle. Moreover, any two of these two perturbations of such perturbations produce cobordant pseudo-cycles. And because of this statement, we know that the free part defines a pseudo-cycle. In particular, this produces an integral homology class in an obvious way. Okay. So this part of the statement says that there is a perturbation scheme to produce pseudo-cycles, and the outcome of this perturbation is some sort of invariant of this derived orbifold chart. And for the purpose of Floer theory, if we consider a pair of derived orbifold charts such that for each of them we found a perturbation, which as a FOP perturbation, it's strongly transverse. The statement says that this perturbation is multiplicative in the sense that so is their product or sum, in the sense that let's take the NBN orbifold to be D1 cross D2, and let's take the obstruction bundle to be the direct sum. And let's take the direct sum, the sum of its two sections. So the assertion is this guy is also strongly transverse. So let me just comment on about this notion of strongly transverse. It's not transversality in the usual sense. It's complicated. I can spend another hour to explain its definition. So it's not obvious at all to prove that their product is transverse. And that's the point why we have such a statement. Okay. So this is about some kind of abstract perturbation scheme. And let me tell you some kind of context of something being normally complex. And perhaps after telling you this, you could see perhaps such a perturbation scheme could work in some more general settings, provided that one can construct, say, global coordinate charts and smoothings on moduli space of J-holomorphic curves. So the claim is the following. So well, this is not actually true on the nose, but let me just say this as some kind of advertisement. All moduli space of pseudo-holomorphic curves are normally complex in some sense. But of course, I would say I'm pretty sure it works for, say, curves entering, say, Guangbo theory, Hamiltonian Floer theory, and Lagrangian Floer theory. But this, I think one needs to be more careful in the SFT setting. So, but for this, you can save the questions for later discussions. So let me try to convince you why this statement makes sense in the settings I said before. So let me give you an explanation in the case of genus zero curves. So normally complex, it means that for points with non-trivial stabilizer, the normal direction of its tangent space has a complex structure. And for moduli space of J-holomorphic curves, points with non-trivial isotropy really come from multi-covered spheres, at least in genus zero case. Non-trivial isotropy is caused by multiply covered spheres. And if we have such a sphere, which is multi-covered, which causes this kind of non-triviality of isotropy, let's say we take the underlying stable map. So our sigma is some kind of nodal Riemann surface. And let's try to look at the associated deformation complex. Then my claim is the gamma non-invariant part of the deformation complex that I will schematically denote it as du coming from sections over this Riemann surface with value in the pullback tangent bundle, the target given by 0, 1 forms, taking value inside same bundle. So the gamma invariant of the deformation complex comes from the spherical components or local, let me say, because for other components, for example, in the case of Lagrangian Floer theory, you consider disks, well, then there's no really non-trivial isotropy contributed from disk components. Sphere components are really the parts where bad things could happen in the sense that it might develop orbifold singularities. And finally, if you consider the restriction of this linearized Cauchy-Riemann operator along the spherical components, is homotopic to a complex linear Cauchy-Riemann operator. Because it's a kind of homotopy, we know that if we take this kind of virtual vector space cooked up from the difference of the co-kernel and kernel and co-kernel of the non-trivial component of this kind of kernel and co-kernel from this kind of gamma U invariant non-invariant part, it's actually a virtual complex space. Vector space. So in other words, you can find a vector space such that the direct sum of kernel with this vector space and the direct sum with co-kernel with vector space is, but both are complex vector spaces. So this is a rough reasoning of why normal complex structure might be the correct thing to consider in the setting of J-holomorphic curves, because at least in genus 0, if we don't have punctures on our curve, essentially all the moduli spaces would have such a structure. So let me just say that as a result, so once the moduli spaces are regularized to have smooth structures, of course, that's a big if, because a lot of hard work is really carried out to endow the moduli spaces with smooth structures. Then our perturbation scheme can be applied to define integer value counts in some very general settings. So as I said before, it can be applied to the setting of defining Lagrangian Floer theory over Z mod 2 or Z, depending on the orientation assumption you put on your Lagrangian. And on the other hand, there's a lot of recent works, recent advances in Hamiltonian dynamics about reducing to finite characteristics. So, but the applications so far are restricted to settings where Hamiltonian Floer theory or corresponding invariants can be defined over integers using classical methods. But now we have some other ways to define integral valued invariants using this kind of perturbation method. I think it's conceivable that it could find applications in some other settings. Okay, so I think it's a good time to stop. So thanks for your attention. We have a host. Okay, let me host myself. So any questions?
May I ask a question? So could you go please to this slide with PSS?
Yes. PSS. Oh, right. Yep.
Yeah. So so the next one, I believe. So when you say that it is injective.
Yeah, injective. Yes.
Yeah. So can you say something about co-kernel? So how much it's not surjective?
So I think it's actually expected to be isomorphism. So right. I mean to prove it's an injection. Well, if we compose curves in this way, it's easier for us to construct out the corresponding global charts. But if we compose curves in the other way, well, there's something more we need to say. But in principle, it could be done. For example, if we prove some kind of invariance independence result of the Hamiltonian Floer theory on our Hamiltonian. So proving injection suffices for proving lower bound. But my claim is once we understand these moduli spaces better, I mean the opposite composition, we could enhance this injection to isomorphism.
And can you, in one sentence, say so why this space is more complicated than the previous one?
Yeah. So for this, what we do is, of course, we all know that the PSS equation, well, is produced from, say, we look at J-holomorphic curves. Well, the solution to Floer equation defined over this kind of once punctured sphere. So ds. So this inhomogeneous term gets turned off near this kind of region, which is close to the origin. And in our construction, what we do is we take fiber product of this moduli space with moduli space of Morse trajectories using the evaluation map. And similarly, we can construct the same thing for the SSP. So to show that it's an injection, what we do is we need to glue these two things together. So in the complement of the shaded region, it solves the Floer equation. And what we do is we slightly, we gradually turn off the perturbation from this kind of Hamiltonian term to get configuration like this. So this is genuinely J-holomorphic. And we do fiber products with Morse trajectories. So this chain map produced on Morse homology is of upper triangular form. Okay, so I just sketched a construction to prove that this is chain homotopy. So this composition SSP PSS is chain homotopy to identity plus something with positive energy. So presumably, we want to do the same thing in the other direction. So at least I haven't figured out a clean way to characterize this kind of behavior. I mean, of course, here we have this kind of semi-infinite Morse trajectories, and in this kind of cobordism process, we sort of shrink the length of these guys to be 0. And over here, we need to resolve the node to get back to the cylinder. So, I mean, geometrically, it's not so hard to write down what you want to do, but to construct a compatible global charts, I mean, there's something complicated here we haven't figured out. So that's why.
Thank you.
Yeah.
As far as I remember, the people who were doing this proof trying to use polyfold theory found exactly the same problem, that they just proved an injection, but they didn't cope with the other gluing map. They said there was some incompatibility with the strata. I mean, I don't know the details, but.
Yeah, exactly. So that's actually the place where we bought this argument from, and well, so yeah, I mean, it's unsatisfactory from the theoretical point of view. So I think I'm also curious to see how to really carry this out.
Can you explain why do you prefer to use the PSS framework versus like continuation solutions?
So sure. For continuation solutions, we could show that this Floer homology group is independent of the choice of Hamiltonian, but nonetheless, you need a step to do computations to show that you can find the preferred Hamiltonian whose Floer homology computes the Morse homology. And that part, well, at least according to my understanding, would require some kind of S1 localization or some other arguments involving some kind of limit discussion. And at least for us, this might be the technically the easiest way to establish what we want.
Oh, I see. Any more questions?
Yes, I have a question about your statement producing pseudo-cycles. So you have this strong assumption that you have some transverse complex structure on the non-trivial part. And does it make sense to hope for such a statement in a much weaker context, like a symplectic structure or something like that? Or do you really need this complex algebraic structure?
So these structures are defined on the moduli spaces. So, for example, I don't know the context where you can, well, easily say that, well, a moduli space has a symplectic structure that can be useful for producing invariants. But on the other hand, I think we have to use the existence of complex structure, because these structures will allow us to perturb our sections by complex polynomials, which more or less makes this kind of zero locus behave like algebraic varieties. So there we can produce pseudo-cycles by dimension counting.
Yes, I understand. But as far as the statement is concerned, can we hope for such a conclusion under weaker assumption? I mean, much weaker assumption, like more symplectic.
Right. I mean, I'm not so hopeful, but maybe other people are more optimistic. But I don't think so. Yeah.
Okay, thank you.
Mm-hmm.
Any more questions? If not, we can thank Shaoyun Bai again.
Thank you.